First of all, okay, yeah. So we were talking about strengthening mechanisms, and then trying to understand the basic deformation mechanism, and we know the basic deformation mechanism is slip in most of the materials, and if you look at the slip, the most crucial aspect is the number of slip systems which decide whether a particular material is more easily deformable or not. So that is what we were looking at, and if you look at the FCC, there are 12 slip systems which are based on the 110 and 111 plane and 110 direction, and if you look at the BCC, the most close packed plane is 110 and the close packed direction is 111. See, what important thing is that the slip direction should be contained in the slip plane. This is very crucial. So when we say slip, it is a movement of dislocation on a plane in a direction in that plane. So you should not consider any direction which is not contained in the plane. The particular direction, there may be n number of close packed directions, but the direction which is contained in the plane. For example, if I am looking at let us say a cubic crystal unit cell, let us look at any of the unit cell. If this is the unit cell that I am looking at, and the 110 plane is nothing but this plane, isn't it? This is the 110 plane, and what is the 111 type of directions which are contained in this plane, which are nothing but the body diagonals. So if you look at those body diagonals, this is one body diagonal, the other body diagonal is this. These are the two body diagonals which are contained in the 110 plane. So those are the two close packed directions. Though there are a number of close packed directions, how many 111 type of directions possible? 8, obviously, because there are 8 corners in any cell, unit cell. So obviously 8 type of directions possible, though there are some directions which are nothing but is the same direction, one in one direction, another in the opposite direction, like 111 direction and then bar 1 direction. They are nothing but basically the same direction in the opposite direction, isn't it? So if you consider that, there are again one can talk in terms of 4 sets of directions. So here in this particular plane, these are the 2 directions. So if you consider there are 6 parallel 110 type of planes, and each plane containing 2 directions, you end up in 12 slip systems. But because these planes are not very close packed planes, and the directions are also not very close packed directions when compared to the FCC type of system, as a result we can also consider other slip systems which are not really equally close packed, but close packed to an extent which are similar to the other 110 type of planes, and that kind of planes are nothing but 112 and 123. So if you consider those planes also, then total you end up in 48 slip systems. So though the number is very large, their nature of close packedness, if you consider, they are not as close packed as the FCC slip systems are. So that is why BCC is less deformable than FCC. And again, if you come to HCP, there the number of slip systems are much lower. There is only one plane which is the close packed plane here, which is nothing but the basal plane, we call it 0001 plane, and there are 2 planes basically within a unit cell, but both are parallel to each other. So effectively we consider only one plane, and in that plane you have 3 directions possible, 1 1 bar 2 0 type of directions, and so 3 into 1 it becomes only 3 slip systems. So as a result we say this HCP type of systems are those where twinning can occur more favorably than slip particularly because the number of slip systems are very few, and we know for a material to be easily deformable it should have a minimum of 5 slip systems. All this you have gone through. So, if you look at this, why we have gone through all this is to know that deformation occurs by movement of dislocations. Deformation occurs by slip in most of the metallic materials. So, as a result, if we can make this slip more difficult, then the material becomes stronger. If you want, the strength of a material is decided by what? Is decided by how easily you can move the dislocation, isn't it? For example, if you say yield strength, yield strength defines what? It defines the minimum stress that is required to induce plastic deformation into material, isn't it? So, that is indirectly related to the stress required for the movement of dislocations. For example, we define what is called critical resolved shear stress. So, critical resolved shear stress is related to the yield strength of the material. So, if you look at the yield strength basically is a measure of, is a macroscopic measure of the stress required to move the dislocations. So, as a result, if you want to have a material stronger, you should have a higher yield strength. So, if you want to have a higher yield strength for any material, it means that you should somehow increase the stress required for the movement of the dislocation. How do you increase the stress required for the movement of dislocation? If the dislocation movement is made more difficult, then if you want to move the dislocation, you have to put in more strain. And if you need to put in more stress to move the dislocation, we can say the material has become stronger. So, strengthening mechanisms are all those mechanisms which make the dislocation movement difficult. So, that is the philosophy of strengthening mechanisms. So, once people have understood that dislocations are the ones which are causing the deformation, then people started looking at how to make the dislocations movement more difficult, so that we can make the material stronger and stronger. But at the same time, the moment you start making the material stronger and stronger, you are also losing on one count, which is nothing but the deformability of the material. The material becomes stronger but less deformable. Obviously, we know both cannot go hand in hand, because the deformability is related to dislocation movement, and the easier the dislocation can move, the more deformable the material is, and the strength of the material is related to how difficult it is for the dislocation to move. So, obviously, both of them cannot be cannot live together. So, as a result, we see the moment we make a material more deformable, its ductility usually falls down. But there is another parameter which we talked when we were talking about the titanium based alloys, which measures to some extent about the difficulty for the materials to fail, that is called toughness. This is something which is different from the ductility. One can have high strength at the same time high toughness. One such example we will see is the grain boundaries. So, people have shown that one way to achieve high strength at the same time high toughness is to make the grain size finer. So, if you look at pure metals, what are all the different strengthening mechanisms in pure metals? As you can see, one first and foremost is that we know there are dislocations in the material. If we can increase the number of dislocations inside the material, then dislocations themselves can act as obstacles for the other dislocations. It is similar to imagining when there is a huge crowd trying to come out of a movie theater. Obviously, the rate of flow of the people out of the gate becomes restricted. So, it is almost like that. So, when you have too many dislocations inside the material, then each dislocation movement is hindered by the existence of the other dislocations, and that is how you can have more obstacles for the dislocations. And how do we do that? We know dislocations can be generated, and when you deform a material, we have dislocation generation coming because of a special type of a mechanism called what? Frank-Reed source. So, there are a number of Frank-Reed sources available inside the material. every material whichever has some inclusions in it always act as Frank-Reed sources, and because of which you can generate dislocations. And for generating dislocation you need to put in some strain into the material. So that is why we call it as, when you deform a material to some extent, during this deformation process you are generating more dislocations, and these extra dislocations that have been generated will act as obstacles for the existing dislocations, and as a result the stress required for further deformation increases, and this is what we call it as strain hardening or work hardening. So work hardening or strain hardening is related to the dislocations, and this is given in terms of, if you want to see how the yield stress is related. This gives you an idea of what is the relation between the yield strength and the dislocation density rho. Here rho is the dislocation density and sigma 0 is the what does it measure? Friction stress. What does it mean physically?
Stress required to move a dislocation
in a single crystal. If you assume that dislocation density is 0, then sigma s becomes sigma 0. So you can consider sigma 0 as the yield stress of a material without any dislocations. So if you keep on adding dislocations to the material, you can see there is a direct relation between the yield strength of the material and dislocation density. But at the same time, when you make the dislocations 0, this formula does not really hold good. What does it say? If you look at this formula more closely, it shows that the yield strength, if you plot it as rho square, there is a straight line relation, isn't it? And here you should see this alpha is nothing but a constant of the order of around 0.3 to 0.6, G is the shear modulus, B is the Burgess vector. So this alpha GB will be the slope of this curve if you plot sigma s versus rho to the power half. If you look at that, when the rho becomes 0, this is what is basically sigma 0, isn't it? And that tells you that if there are no dislocations, the yield strength of the material is lower than what you have when you have dislocations, which is not really true. When you look at whiskers which do not have any dislocations at all, that means perfect crystals without any dislocations, their yield strength is much higher, which we call theoretical cohesive strength. And so the moment you put a small number of dislocations in that, the strength drastically drops, because now the deformation occurs by dislocation movement, and when there are no dislocations, how does the deformation occur? No, when there are no dislocations at all, it is not even twinning. It is the shearing of atoms one over the other. It is like pack of cards. So when you think of atoms which are arranged as atomic planes, you imagine one atomic plane shearing over the other atomic plane, and that is how the deformation occurs in a perfect crystal without any dislocations, and that needs a much higher stress of the order of few gigapascals when compared to the actual stress required for the movement of dislocation. The yield strength of most of the metals are of the order of few MPa. For example, aluminum, if you take aluminum, yield strength is of the order of how much? About 40 MPa. Whereas if you look at the aluminum without any dislocations and think of what will be the yield strength of that, or what will be the strength of that theoretical cohesive strength, that will be of the order of few gigapascals. So there is a sudden drop in the strength from the gigapascal zone to a megapascal zone by almost 3 orders or 2 orders at least when you introduce dislocations into the material. So as a result, this particular plot does not really hold good in this domain. when the rho tends to 0, this particular equation what we have written here does not work. And so that in principle you will see should go more or less exponentially up in that zone which is very close to 0 dislocation density. This more or less goes very steeply up and reaches the value of theoretical cohesive strength when the dislocation density goes to 0. So, in a small domain which is close to omega tending to 0, this particular equation does not work and it deviates from this linearity. Otherwise, when you have large number of dislocations, this usually works very easily. So, that one has to remember that. So, there is a relation between the yield strength and the dislocation density which works when you have more than a few dislocations, but when you have very little number of dislocations. This is one of the reasons why people say in nanocrystalline materials, how do we talk in terms of the Hall-Petch relation. People talk about it. There is always what is people call nowadays as lattice softening can occur in nanomaterials because the number of dislocations itself can be so few. So, how do we represent the strengthening of nanomaterials when we come to grain boundary strengthening? This becomes an issue. How do we talk in terms of strengthening because of dislocations? Probably there is more of grain boundary sliding when you have very few very small grain sizes of the order of around 5 nanometers or even less than that, because as you know that there has to be a minimum distance between any two dislocations. Any two like dislocations should have a minimum distance between them, because there is always a repulsion between like dislocations. So, as a result one has to maintain a certain distance between them, and if you think of about 5 nanometer length as the diameter of a particular nanomaterial, within that 5 nanometer, if you can imagine what is the distance between any two dislocations, it is of the order of around 5 interatomic distances. If you consider about 5 interatomic distances and an interatomic distance of the order of around 4 angstroms, if you consider, then 5 interatomic distances becomes almost equivalent to 2 nanometers. So, that means in 5 nanometers you can hardly have about 4 or 3 dislocations in one direction. One can imagine what is there in the total volume, that is a different thing, but in a particular direction one cannot think of more than about 3 or 4 or 5 at the most. So, with such few dislocations, how can we really imagine a lot of strengthening coming because of the Hall-Petch relation? We know that usually strength keeps on increasing when you decrease the grain size. So, we will come to that. So, this is what is basically strain hardening, where because of the dislocations one can generate. The next type of hardening in pure metals, we are all talking of pure metals at this moment. We have not added any alloying element at the moment to generate any additional type of strengthening. So, in pure metals the other type of strengthening is basically the grain boundaries. So, they are the other type of obstacles, because when we think of a slip plane cannot be extended beyond the grain boundary. Obviously, grain boundary is a limit which distinguishes one grain from the other, and how do we distinguish the two grains? With their orientation. We say there is an orientation difference. If there is an orientation difference, definitely that means the slip plane, let us say if we are considering 111 plane, 111 plane orientation in one grain is different from its orientation in another grain. So, if I am considering two grains, grain 1 and grain 2, if in grain 1 if all 111 planes are oriented in this direction, and grain 2 they are oriented in a different direction. Otherwise, we cannot call them as two grains, we should call them as only one grain if there is no difference in the orientation. So, as a result, if a dislocation is moving on this plane, the moment it comes here it has to stop, because the plane is not continuing further. So, it has to stop, and then you have to put in more stress so that you can induce dislocation movement on the other plane on the same type of 111 plane in the other grain. So, as a result the stress required will be higher, and this increases if you increase number of such boundaries. So, what is the way to increase such number of such boundaries? By making the grains finer. If we can make the grains finer, we can have much more obstacles for the dislocation movement, and this is usually given by an expression like this. Which is usually called as the Hall-Petch relation. All of us are aware of it. So, yield strength is related to the d to the power minus half by a relation which is similar to this. So, if I plot the yield stress versus d to the power minus half, it looks something like this. As d to the power minus half increases, d to the power minus half increasing means what? D is decreasing. If the d decreases, the strength increases, and the intercept here represents sigma 0 within nothing but the yield strength of what? Of single crystal. Obviously, you imagine when d to the power minus half goes to 0, what are we talking about? It is a large grain, very large grain, in principle whose grain size is infinite. That is the type of a grain that we are talking about. That means it is a single crystal without any grain boundaries. So, if you can imagine a grain without any grain boundaries, the grain boundaries are so far off that we cannot physically see them in such a, and you start seeing only the surface of the material before seeing the grain boundary. So, in such a material which is nothing but a single crystal, so you can talk of this as the yield strength of that single crystal. And nowadays people say that when you go to very fine grain sizes, there is a possibility of the yield stress dropping, and that is what we call as the lattice softening. Though it has not been really proved in a number of systems, there are few experimental evidences that are available where people see that there is a possibility of some decrease in the strength like that. So, this is the what is called grain boundary strengthening. And how do you make the grains finer? And what is the grain refinement basically means? I am giving you some examples of this. If you look at a typical casting when you take a liquid metal and solidify into a mold and look at the cross section of such a cylindrical casting, the grain structure looks like this. This is what is called a macro structure, and we know usually that the grains are nucleated at the where? At the mold wall, and you will get innumerable number of those nuclei there, and some of these nuclei start growing into the interior, and we call those fine grained structure at the mold wall as the chilled zone, and then you have this next zone called columnar grains, which go either up to the center or to certain extent depending on the type of material that we are considering, and also depending on the type of thermal conditions there. If there is a high undercooling, there is a possibility of some other grains nucleating at the center, such as some coarse equiax grain structure. Otherwise, usually you have these columnar grains going almost up to the center, and this is a typical grain structure. And once you can achieve a grain refinement in this material, you can see the grains will be very fine, uniformly distributed grain sizes, more or less homogeneous fine grain structure. And how do you achieve it? There are a number of ways, and before we go to that, we should see what do you achieve by doing that. As I told you, strength can be increased. We have seen Hall-Petch relation already, and toughness can be increased. This is the only way by which you can increase both the strength and the toughness. How toughness can be increased is because when you have a large number of grain boundaries, when a crack is nucleated, the path for this crack propagation becomes more tortuous. the crack has to propagate along these grain boundaries, and when you have large number of these grain boundaries, the crack propagation becomes more difficult, particularly in metallic materials. If you have brittle materials such as ceramics, then anyway there is no cohesion at the grain boundaries, so as a result the crack propagation very easily occurs at the grain boundaries, which and gives you what is called intergranular cracking in brittle materials, whereas in metallic materials usually the cohesion is not that poor at the grain boundaries. And so if you have some good cohesion at the grain boundaries, if you can increase these grain boundaries, you are increasing the number of obstacles for the crack propagation. As a result, one can increase the toughness. So the toughness can be improved, the machinability can be improved, particularly in case of castings. It is very crucial that machinability is a function of the grain size. If you have fine grains, you can have much easy machinability, because the chips becomes very fine, so that easily it can be machined and one can achieve good surface finish very easily. And finally, one can have very fine uniform distribution of microporosity and second phase particles. What is this microporosity? Microporosity comes because of the solidification of the liquid metal at the interdendritic region. We know that whenever a liquid is solidifying, the solid nucleates as dendrite, and at the interdendritic regions you have some liquid left out, and this liquid is the last liquid to solidify, and when it is solidifying there is a shrinkage always, because liquid occupies usually a much higher volume than the solid. So as a result you have the shrinkage on a uniform scale which occurs at the interdendritic regions, and this is what is called microporosity, because it is porosity which you get because of this shrinkage, and because it is on the micro level we call it as microporosity. And if you can have a large number of fine grain material, so that means this liquid is distributed on a finer scale more or less uniformly, so as a result this microporosity is also distributed on a much finer scale, instead of having on a large pockets of porosity in fewer locations. You have a much more uniform distribution of microporosity, that gives you much higher strength. How do you achieve this? There are a number of techniques. First technique, which we have talked a lot earlier also when we are talking of rapid solidification processing, RSP, the first most important technique is rapid solidification. And we know when we rapidly solidify, what do we achieve? High undercooling. Once we achieve high undercooling, then you have high nucleation rate and small critical nucleus, and that is what gives you fine grains. A smaller critical nucleus and a higher nucleation rate is what we achieve by high undercooling, and that gives you fine grain structure. And the second possibility is what is called mechanical vibration of the liquid. There are different techniques nowadays available: Thixo casting, Rio casting. These are all different casting techniques where you take the whole casting and then vibrate this, and when we vibrate it, what happens is the dendrites which have nucleated and start growing into the liquid, they break. So instead of a columnar grain, the columnar grains break into fine grains, so and then they get distributed uniformly in the liquid, and so that you get a fine grain structure. So here you are not really increasing the nucleation rate. What you are doing is you are just breaking the already grown nuclei, and because of this breaking, each of the dendrite is broken into a number of parts, so that the number of grains have increased. So you are multiplying the grains by breaking the grains. This is similar to the high energy ball milling, where you are taking a big crystals, breaking them into nanocrystals. Though you do not really achieve nanocrystals here, you can at least break columnar dendritic grains into more or less uniform grains. But the problem is this kind of a technique is very difficult to be used when you have large castings. If you have large castings, a huge ingot is there, you want to really use this technique, the whole ingot has to be placed on a vibrating platform, and the whole thing has to be vibrated. Obviously it is not feasible practically, so only on small casting sizes this is achievable. The most popular technique is the what is called heterogeneous nucleation or inoculation, and which is very commonly used in a number of systems, and particularly in iron based systems and aluminum based systems. This has been very successfully adopted by a large number of investigators. These are all in the liquid state we have talked about so far. One can also achieve fine grained structures in the solid state. That means obviously whenever I am saying fine grain sizes, we are talking of solid state only, but the first three techniques are by controlling the solidification, whereas the last three techniques are in the solid state itself, how to refine the grain size. One is by adding growth hindering agents after recrystallization. First of all, recrystallization itself is a way to refine the grain sizes, which is used in a number of wrought alloys, particularly in case of cast alloys, because we do not deform the alloy. As a result, you cannot use these solid state processing techniques. That is why one has to adopt only these first three techniques, because once the casting is obtained, you do not do anything else with the casting excepting giving a good surface finish to the casting in case of castings, whereas in case of wrought alloys we are going to deform it. So as a result, one can use recrystallization as a process, and one can also put certain growth hindering agents at the grain boundaries. For example, we know about high strength low alloy steels, HSLA, or microalloyed steels, where people add certain particles, precipitate particles, which can act as growth hindering agents called pinning agents. So Zener pinning. So because of the Zener pinning, one can achieve much finer grain sizes. The other technique which people have used, particularly in steels, is what is called cyclic heat treatment. The philosophy here is, when you take an austenite and start cooling it between the A1 and A3 zone, what is that called? Intercritical zone. Okay. So in that intercritical zone, if you start cooling it, what do you get? When a austenite is cooled through the intercritical zone, what do you get? Proeductide phase comes out. Okay, whether it is hypoeductoid or hypereductoid, depending on that, some proeductide phase comes out. So particularly in case of the hypoeductoid alloys, this has been very successfully used, where ferrite comes out, and when an austenite grain is there and ferrite is nucleating, and how many grains you expect out of one austenite grain? How many grains of ferrite do you expect? Is it one or more? Imagine an austenite grain is there. This is austenite, and when this is being cooled, what do you expect the ferrite grain size to be? Will it be equal to that of austenite grain? Basically, because we know grain boundary acts as a nucleating site, as a result a number of nuclei can nucleate on the grain boundary in different regions. And if a number of nuclei can form, all these grow and finally cover up the whole of austenite. So as a result, each of this austenite grain is broken into a number of ferrite grains, and at room temperature, what are we bothered about when we talk of grain size? It is the ferrite grain size that is important to us, not really the austenite grain size, because the actual deformation occurs if we are talking of room temperature strength of a steel. Room temperature strength of the steel is related to the ferrite grain size and not related to the austenite grain size, isn't it? So as a result, we know that austenite gives one austenite grain gives a number of ferrite grains. And now if you take this ferrite which is there in the intercritical zone and start heating it very rapidly, we know that each grain of ferrite will transform into one grain of austenite, because you are heating it very rapidly, and because of which the whole grain of ferrite transforms to the austenite grain. So what happens if you take a situation like this, which is having a large number of grains, let us say like this, and this particular situation, if you start heating it, it becomes again all of these grains which are here get transformed to austenite. Okay, there are probably inside also some grains, we have not considered that still, maybe. So, whatever grains that are there, the ferrite grains, alpha grains, all alpha grains get converted to gamma grains. Now, you can see with this what we have done is that you are starting with one grain of austenite, you have cooled it to some temperature in the intercritical zone and then heated back to austenite very rapidly, and while doing that you have come back to the austenitic regime with a larger number of austenitic grains. Starting with one grain of austenite, now you have generated a larger number of austenite grains, because all of these ferrite grains have converted into austenite grains. And now if you can again cool these austenite grains, which are there larger number of them, each one of these austenite grain can nucleate more number of ferrite grains again, and again if you heat it rapidly, again all of them get converted to ferrite austenite grains. Like that, if one can do in a number of cycles, 2 or 3 or 4 or 5 cycles, one can ultimately end up in very fine ferrite grains. And people have adopted this technique in a number of cases where grain size is a crucial aspect, because definitely this means some economy has to be considered, because obviously you are doing cyclic heating, so you are putting in more energy into the system, so obviously some cost is involved in this process, but if that cost is going to give you a much finer ferrite grains, which is going to improve your strength dramatically, so people can go for that. So this has been a technique where people have really used it. But among all these techniques, the most popular technique is the inoculation. Number of people have done this, and in our own group we have also done it in a very vigorous fashion over the last 10 years, and particularly the grain refinement of aluminum alloys. Aluminum alloys, every aluminum alloy that comes out of an aluminum industry is invariably grain refined by inoculation, and this inoculation is done by usually alloys such as aluminum titanium boron type of alloys. For example, the most popular alloy is called aluminum 5 titanium 1 boron, which are called master alloys, and these alloys, if you look at the composition, it has titanium and boron, and titanium reacts with aluminum and gives you TiAl3 particles, and titanium and boron, when they are together, they react with each other and form TiB2. So you have two types of particles, TiAl3 and TiB2 in this type of a master alloy, and when you take this master alloy, add a small piece of it to a liquid aluminum. What does this master alloy contain? This master alloy basically contains aluminum matrix. You can see this is the aluminum matrix, and the particles such as TiAl3, you can see different sizes of TiAl3 particles here, and TiB2 particles are much finer, of the order of around less than 1 micron, 0.5 micron or so, such type of TiB2 particles. So you have a matrix of aluminum and fine TiAl3 and TiB2 particles. So if you take a piece of this master alloy, add it into a liquid aluminum, what you see is that the matrix which is aluminum melts away, because you have put it into an aluminum alloy. So obviously this matrix which is aluminum immediately melts, and the TiAl3 and TiB2 particles get suspended in this liquid. So you have a liquid aluminum now, in which you have added this master alloy pieces, and master alloy pieces, out of that whatever alpha aluminum which is the matrix is there, which dissolves, and TiAl3 and TiB2 particles get suspended, and this liquid containing this suspension of these particles, if you pour it into a mold, during the solidification these particles act as nucleating sites, and for a particle to act as nucleating site, there are a number of conditions have to be met. What are the conditions? First and foremost is that the structure of the particle should be similar to that of the structure of the solid that is coming out. there has to be some kind of an epitaxial relation. That means either the structure should be exactly the same or at least it is similar. For example, if you look at TiB2, TiB2 has a hexagonal structure, and aluminum, which is the for aluminum alloys we use these things. So aluminum is an FCC. So obviously there is some relation between HCP and FCC, particularly if you look at the basal plane. The basal plane has a similar atomic arrangement as that of 111 plane in FCC. So there is a lot of similarity between 111 plane of FCC and the basal plane. So basal plane can act as a nucleating site for the 111 plane of the FCC. And similarly, TiAl3 is a BCT type of structure, DO22 type of structure. We have talked about this Al3Ti, and it also has some planes which have some similarity with aluminum. So it can also act as a nucleating site for aluminum. So if you add this kind of particles to it, they act as nucleating sites, and once these particles are uniformly distributed throughout the casting, you will have grains nucleating at each of these particles, and then as a result you will have ultimately the whole casting gets converted to very fine aqueous grains like this, and that can be shown in terms of the grain sizes if one can measure the grain sizes. But usually when you add a grain refiner to the aluminum alloy, there is a minimum time that is required for the grain refiner to act as a grain refiner. This is what is called contact time, optimum contact time. What happens is when you add a grain refiner to the liquid and immediately pour that liquid into a mold and cut it after it is solidified and look at the grain size, you do not get very fine grain size. You have to hold these particles inside the liquid for some time, so that these particles get uniformly distributed into the liquid, and that particular liquid, when you pour it into the mold, they start acting as nucleating sites. So as a result, if you plot the grain size after holding the grain refiner into the liquid for different amounts of time and then pouring the liquid into the mold, cutting that casting that you obtain and then looking at the grain sizes. So after different holding times, if you look at it, you will see the grain size keeps on decreasing initially up to certain time, and then later if you hold it again, you start seeing that the grain size further increases. And this contact time, optimum contact time, is very crucial for any grain refiner. It keeps on changing for grain refiner to grain refiner, and one can control it by controlling the microstructure of the grain refiner. Particularly, it depends on the size of the particles. If the particles are very fine, then these particles immediately act as nucleating sites. If the particles are very big, usually big particles never act as nucleating sites. So when you hold these particles inside the liquid, they usually what happens is the particles start dissolving into the liquid, because Al3Ti is soluble into the aluminum. So if you hold it inside the liquid, after some time the particles dissolve to some extent, so their sizes decrease, and once they decrease to certain size, then they start acting as nucleating sites. So as a result, there is a certain optimum contact time. But if you hold it for a long period, then what happens is that there are two things that happen. One is that these particles may completely dissolve into the liquid. If they completely dissolve, then what happens? You do not have any particles. If you do not have any particles, you pour that liquid into the mold, so there are no heterogeneous nucleating sites. So there is no grain refinement that you can achieve. Second point is also that these particles are usually heavier than the liquid metal. For example, TiAl3 or TiB2, if you look at it, their densities are of the order of 3.5 and 4.2 or so. For example, TiAl3 is about 3.5, TiB2 is about 4.2 or so. So if you look at this kind of high densities when compared to liquid metal density of aluminum is about 2.4. The aluminum is 2.7, but when you liquefy aluminum, the densities are much lower. In fact, it's about 2.35 or 2.4. So with that density, if you compare these particle densities, particles are denser. So if you hold it for a long time, they settle down. If they settle down, if you pour the liquid into the mold, so obviously the top liquid which you pour will not contain any particles, so they will not act as nucleating site. So as a result, what is crucial is that one has to identify this and how to control this fading. In this connection, the grain refiners are usually broadly classified into three groups. One is called a slow acting grain refiner. This is number 1, which you see here. That means this takes a long time for it to act as a good grain refiner. And the second type of grain refiner is called fast acting grain refiner, but early fading grain refiner. That means if you keep it inside the liquid metal, within a very short period it acts as a good grain refiner, but if you hold it for a long period, it loses its efficiency. And the best grain refiner is what we call the ideal grain refiner, which is called fast acting and long lasting. And this is crucial, and this can be achieved by proper control of the particle sizes. If you have a good combination of fine and coarse particles, the fine particles act as good nucleating sites within a very short period, and the big particles will act as a nucleating sites on longer holding. So as a result, you can have a good combination of both, and that's what we have achieved, and try to compare with what is commercially available. Most of the aluminum industries import the grain refiners. These aluminum, titanium, boron, master alloys, they are all imported from basically one company called London Scandinavian Metals. This is a very popular company which sells grain refiners to all these Nalco, Balco, Hindalco. You take any aluminum company, they all buy from that. Okay, and in this particular institute or our department, we have developed a grain refiner, which when you compare with this particular grain refiner, these are all aluminum alloys, pure aluminum, for example, without, this is not an aluminum alloy, basically aluminum, commercial purity aluminum, and without any grain refiner, these numbers which are given are time of holding, 0 minutes, 2 minutes, 5 minutes, 30, 60, 120. So if you hold it for different timings, you can see initially you get good grain refinement, but on long holding, this particular grain refiner is not good. You see, start seeing the grain size starts increasing from here to here. Whereas here you can see the grain size is maintained even after 120 minutes. We have even tested up to 3 hours of holding. Okay. Why do you need to test for long hours? Because basically when you take aluminum foundries, the way people do grain refinement is they take the liquid metal in a ladle and put the grain refiner into that ladle, and now you start pouring that liquid metal of the ladle into different molds, and sometimes you may have to pour into a large number of molds. So from the first mold to the last mold, the time of the pouring might even take about 2 to 3 hours. So as a result, the last liquid which you are pouring should have sufficient number of nucleating sites present in them, so that it can act as a nucleating site, whereas some of the grain refiners do not work that way. So one has to consider this aspect, and this is where we can say that we have been quite successful in this. This particular technology has already been patented. One company in India has already started making them on a large scale and started selling to Nalco, Balco and Hindalco. So this is a real proven technology which has come out of our department. And if you look at the grain sizes and the alloy which is made here, which is called alloy A here, has much lower grain sizes than either London Scandinavian Metal or the Anglo Blackwell. So if you use any of these grain refiners, you don't get very good grain refinement. Okay, though they are also commercially used, but this is much better and much cheaper grain refiner than any of these commercial master alloys. We will stop here and look at the other strengthening mechanisms in the next class.